So we have looked at the corrective fields in large scale yielding when there is no hardening in the material. For a rigid perfectly plastic material, we have looked at the slip line fields, and from the slip line fields we have been able to calculate the stresses in different sectors ahead of the crack tip that we have done in the last class. Now we will shift to a more realistic material, which is a hardening material, but we will still assume that the elastic strains in large scale yielding, at least in front of the crack tip, are negligible in comparison to the plastic strains, and therefore the entire strain is plastic strain, or plastic strain is the entire strain and elastic strains are negligible. We had already visited this assumption when we did plasticity. Remember, we did deformation theory of plasticity, and if you go back to your in your notes, um, we had looked at this particular relationship. So the flow rule in case of deformation theory of plasticity, remember in deformation theory of plasticity, we had assumed that the material is never unloaded. It is continuously loaded. So stresses are always increasing at the material point, and therefore the material behaves like a nonlinear elastic material. There is only one branch of the stress strain response, which is a stress increasing and strain increasing. So in that situation, we can actually find the flow rule in terms of a total stress, a total deviatoric stress, and the total plastic strain. So in general, for incremental plasticity, we had a flow rule which was of this form for the von Mises material, whereas for deformation theory of plasticity, where we discount the of possibility of unloading, this is the flow rule, and it's now not in terms of increments in stress and strain. It is now in terms of total stress, and total strain. Uh, if we neglect elastic strains, then this is entirely the entire strain is plastic, and then we have this relationship for deformation theory of plasticity for the total strain, all of which is plastic. And remember, this quantity n is the hardening exponent, which was part of the Ramberg-Osgood stress strain law, which fits many ductile materials. And as n increases, you move towards perfect plasticity. As n decreases towards 1, you move towards a perfectly elastic material. So we are going to use this concept. We are going to use this expression now to figure out what happens to the crack tip fields, what are the stresses and strains at the crack tip fields in front of the crack tip when there is a hardening material present and elastic strains are negligible. So to do that, we have to go back to our old friend, the J integral, and we will look at the J integral on a circular contour of radius r, ahead of the crack tip. So this is the contour that we are going to take, and on this contour I define an angle theta, and I'm going to calculate the J integral on this contour. Now remember, the J integral in 2 dimensions, we'll again assume 2 dimensions, is this, where gamma is the contour that I have just shown, and ds will be r times d theta, assuming that the thickness in the z direction, x3 direction, is unity. So also I need the normals. So these normals have components n1 equal to cos theta and n2 equal to sin theta. So these are the normals, and then the non-zero stresses are sigma 11, sigma 22, sigma 12, and sigma 33 is also non-zero for plane strain. So let us now, with these quantities, let us try to write down the J integral for this circular contour. Okay. Now, when we do that, we first take the n beta inside. So here we have W n1 minus, so this term is this and this is Wn1, and that's what we have written here. And we have separated this into two terms. So here we have separated it into sigma alpha 1 n1 u alpha comma 1 plus sigma alpha 2 n2 u alpha comma 1. So we have separated this into two terms and written them separately. The n1 terms together. So n1 is cos theta. So this term expands to sigma 1 1 u 1 comma 1, sigma 1 to u 2 comma 1, and this term expands into this. N2 is sine theta, n1 is cos theta. So this is what you have. Now on the circular contour, the traction, this traction is, remember, T1 is sigma 1 1 n1 plus sigma 1 2 n2. T2 is sigma 1 2 n1 plus sigma 2 2 n2. N1 is cos theta, n2 is sine theta. So I can write T1 and T2 in this form, and then I can replace this. I can replace these terms with u1 comma 1. So this term with u1 comma 1 and this term with u1 comma 1, sigma 1 1 cos theta plus sigma 1 2 sine theta, that is my T1. So u1 comma 1 goes with T1, and then sigma 1 2 cos theta, sigma 2 2 sine theta, that goes with T2. So T2 u2 comma 1, u2 comma 1 goes with T2, u1 comma 1 goes with T1. So this is my J integral on the circular contour, and I can write it, if I want, as WR theta cos theta, which is this, minus T alpha u alpha comma 1, which is these two terms. So this is my J integral. Two things are to be noted. I have taken a circular contour of a fixed radius r, and ds is r d theta. The r comes out of the integral, and I integrate from minus pi to pi, which is from here to here. So theta goes from minus pi to pi. The second thing to note is that remember what W is. W was defined through this relation. W is a function of strains, and we assumed, when we derived the J integral, we assumed that a function, scalar function W exists, so that its derivative with respect to the strains give you the stresses. Now, it turns out that for incremental theory of plasticity, where you have a relation between increments of stress and increments of strain, RW cannot exist, because incremental theory of plasticity is two branches, a loading branch and an unloading branch, actually three branches, an elastic loading branch, a plastic loading branch, and an unloading branch. So it is not a single function, it is not a smooth function, and therefore W does not, the existence of W is not guaranteed. Whereas we have assumed a deformation theory of plasticity where there is no unloading branch, and deformation theory of plasticity behaves exactly like a nonlinear theory of elasticity. And because we have done that, we can assume that a W exists, so that its derivative with respect to strain gives you the stresses. So the reason for taking deformation theory of plasticity into account is twofold. That when you are loading the crack, the stresses in front of the crack are always increasing. There's no unloading unless you are doing fatigue or something of that sort. That's the first thing. And the second thing is that it it sort of allows you to assume the existence of a strain energy density function. The strain energy density function is no longer quadratic, it is something else, but it exists. We can think that it exists, and the stresses can be derived as derivatives of the strain energy density function. Okay, so that is why we are using deformation gradient of plasticity, deformation theory of plasticity in this derivation. So now the logic goes like this, the argument goes like this. This R has come out of the integral, and we know that J is contour independent over this minus pi to pi contour. It should be contour independent. It should not depend on R. So this quantity here, must have a form of f theta by r, so that this r and the r below cancels out, and you have a function of theta only, which does not depend on the size of the contour. So what we infer from here is that this quantity has to vary as some function of theta divided by r. So this quantity has dimensions of 1 by r and a function of theta. So let us look at it a little bit closely. Remember that sigma ij can be given in terms of W by this expression that we have seen before. So W has units of sigma ij epsilon ij. So W has units of this. This quantity T has units of sigma ij, and this has units of, these are displacement gradients. So these have these have the same kind of variation as the strains. So this quantity and this quantity are both kind of dimensionally stress times strain kind of quantities. So both of them are stress times strain kind of quantities, and they have to vary as f theta by r. So from deformation theory of plasticity, we have already seen this. This is how the total strain varies with the total stress, in this case the deviatoric stress. Also remember that sigma E is defined as 3 by 2 sigma ij prime sigma ij prime. You have this n minus 1 here, and this tells you that the right hand side goes as sigma ij prime to the power n. Now, if this epsilon goes as sigma ij prime to the power n, then sigma ij epsilon ij will go as sigma ij prime to the power n plus 1, which is same as saying it will go as sigma ij to the power n plus 1, which we have shown from the path independence of the J integral should go as 1 by r. Okay, so if that is the case, then sigma ij should go as 1 by r to the power 1 by n plus 1. So for the elastic case, n is equal to 1. So this goes as r to the power 1 by r to the power half, which is what we have seen for the elastic case. But for the elastoplastic case, the stresses in front of the crack tip should go as 1 by r to the power 1 by n plus 1, where n is your hardening index, work hardening index. So this is what the scaling analysis, starting with the path independence of the J integral, gives us. It tells us that in the hardening case, in front of a sharp crack, just like we did in the Williams solution for the elastic case, the stresses in this region in front of the crack tip should go as 1 by r to the power 1 by n plus 1. Okay, so now how would the entire stress field at the crack tip look like? In analogy with what we have seen in the Williams solution, we can assume that sigma ij will depend on angular function, will depend on an angular function and will depend on a function of r which goes as r to the power 1 by n plus 1. And epsilon ij will epsilon ij, remember, is sigma ij to the power n. So epsilon ij now will go as r to the power n by n plus 1. And this is not the stress intensity factor, but this is some amplitude of the singular field that is valid for the hardening case, neglecting all elastic strains. Now, what are these angular functions? What are these angular functions? We don't know yet. What we have only figured out is that sigma ij should go as 1 by r to the power 1, r to the power 1 by n plus 1. Epsilon ij should go as r to the power n by n plus 1. And assuming that there is a dominant term in the series and that is characterized by some amplitude like the stress intensity factor, we have written this K. Now this problem in totality was solved by Hutchinson, Rice and Rosengren, two sets of papers in the same journal, um, in the Journal of Applied Mechanics, in the same issue of the Journal of Applied Mechanics. Two back-to-back papers were published by Hutchinson and Rice and Rosengren, and therefore these are called HRR fields. And what the HRR fields give us is the entire form of this variation. So what HRR fields tell us is that, well, from the path independence of the J integral, we have figured out that this should be the variation in R, but we have not figured out what is the angular variation and what should be this amplitude, what should be the analog of the stress intensity factor in case of hardening plasticity. HRR fields tell us that this assumption is correct, that there is a separable solution. That separable solution is, however, somewhat more complicated than what I have written here, and the full form we cannot develop it in this course for paucity of time, but I'll give you the full form and try to explain the full form of this variation in front of the crack tip. It's exactly analogous to the elastic solution that we have figured out earlier, Williams solution. So what it says is that yes, the R variation should go as 1 by n plus 1. And now instead of k, J integral takes the role of the amplitude of this singular stress function. There are a few other terms. This is sigma y, I'm sorry. So there are a few other terms, alpha, sigma y, epsilon naught. These are terms that are there in the Ramberg-Osgood stress strain relation that we have assumed for the material. So these are material constants that are known. There is one more quantity called In. So the amplitude is J by In actually, whereas In is given through this graph. So as n increases, In actually decreases. For plane strain, this is the variation. For plane stress, this is the variation. But what you see is it's a weak function of n. So it has more or less a constant value. So In is not a very important, In is not going to cause a huge change in the stresses. But what the stress amplitude is now governed by J instead of K in linear elastic fracture mechanics. So J takes the role of K. So this adds another significance to the J integral. J integral does not only give you the energy flux at the crack tip, energy momentum at the crack tip, but it also acts as the amplitude of the stresses in front of a sharp crack. The angular functions now do not have as nice a form as we had in case of elasticity, case of the Williams solution, but they are dependent on theta as well as on the hardening parameter. Remember, if you change n, you change the material as well. So different materials have different hardening exponents. So this angular function depends on theta as well as n. And here are some examples. They have to be they're numerically specified. So for plane strain and plane stress, these are the angular functions in polar coordinates, cylindrical polar coordinates. So this is for r theta. At theta equal to 0, the angular function for r theta is 0, which means that again you have in a mode 1 situation at theta equal to 0, for mode 1 at theta equal to 0, sigma r theta is equal to 0 as it should be. Sigma theta theta is this. So sigma theta theta is the maximum. Sigma rr and sigma theta theta at theta equal to 0 are no longer equal. Uh, but they are close. This is for plane strain. Similarly, for plane stress, the shear stress is 0 at theta equal to 0 for mode 1. And then sigma RR is sigma theta theta is this. It's the highest. Sigma RR is close but not equal, unlike the elastic case. And the plane strain and plane stress solutions are different. This is, of course, I have plotted it for n equal to 3. If you change the value of n, you will get different shapes of the functions. Okay, so these angular functions are tabulated, angular functions are known, and it is possible to find them numerically as well. So this is the form of the stress. Contrast this with K1 by root 2 pi r. This what the stresses in the linear elastic case. These are the stresses at the crack tip, exactly analogous stresses. Now in place of K1 you have the J integral for the problem, and you have this In, which is a weak function of n, and this is how the stresses at the crack tip are going to look like. Now you can you can also find the displacements, and if you again look at the scaling, sigma ij scales as with r as r to the power 1 by n plus 1 by r to the power 1 by n plus 1. Epsilon ij scales as sigma ij to the power n, which means it scales as 1 by r to the power n by n plus 1, right? And this means that uh, epsilon displacements 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 would scale as 1 by r to the power. So to get displacements you will have to integrate this, so this will scale as n by n plus 1 minus 1, which is equal to 1 by n plus 1. And so this will scale as minus 1, which will give you plus 1 by n plus 1. Okay, so displacements scale as r to the power 1 by n plus 1, and this is the whole form of the displacement. These are the angular functions, again dependent both on theta as well as the material, that is n. Now what you see immediately is that ui goes to 0 at the crack tip. As r tends to 0, ui goes to 0. Therefore, for the strain hardening material, you don't have a jump in displacement at the crack tip. So you have a continuous variation of the displacement, which goes to 0 at the crack tip. That is for a strain hardening material. For the elastic material also, the displacements went to 0 at the crack tip, but now with strain hardening the crack expands more, the crack opens more, and therefore the strain hardening case has a wider crack opening than for the elastic case. However, as we saw in the Dugdale model, for the perfectly plastic case there was a abrupt jump in displacement at the crack tip. So For the perfectly plastic case, which corresponds to n tends to infinity, you have a jump in displacement, you have crack blunting. Here you don't have a crack blunting per se. The displacements do go to zero at the crack tip, like in the elastic case, but you can define a blunting, and this is what is generally done when you look at a crack tip. You can define a blunting by subtending two lines at 90 degrees from the tip of the crack where the displacements are zero, and these are 45, this cut the crack flanks at 45 degrees, and then this distance delta t is taken as the crack opening displacement. So you don't have this sharp blunting as you have in the perfectly plastic case, but like we saw for the Dugdale model, but you can define a delta t which is a surrogate for this strain hardening case. So uh, it can be shown that this delta t is related to the this delta t is related to the j which characterizes the crack tip fields in a very straightforward manner, and this can be shown through computations as well as through some theory. uh, So delta t varies linearly with J. So J is like your stress intensity factor for the plastic for the plastic hardening work hardening case. So as you increase J, delta T increases linearly. So J and delta T have a linear relationship. The factor dn varies between zero point 0.5 and 1.07 as n tends to infinity. And for plane strain, for plane stress, this is the variation. For plane strain, it is zero point 0.3 to 0.65 as n tends to infinity. So this is at one, this is close to elastic, and then as n tends to infinity, it goes to 0.65. So there's a one-to-one linear relationship between delta t and j, just like in the elastic case. uh, we had we had said that K1 attaining K1C is the condition for crack growth. Similarly, here we can say J attaining JC is the condition for crack growth in case of a elastoplastic uh, work hardening material. So we can have a JC which is exactly analogous to K1C for the plastic case. Now, since J and delta T, J and this delta T are linearly related, as this equation shows, we can also envisage that delta T going to delta TC is also a viable condition for crack growth in the elastoplastic case. So uh, we can either write a crack growth criteria in terms of a critical crack opening, or we can write a criteria in terms of a critical J integral, critical value of the J integral. Okay, so now what you can see is the nature of the solution is very different. It has a different power of R. However, in many ways, it is similar to the elastic solution. So you have a crack tip characterizing parameter, which in this case is J. You have an angular function. You have a separation between the R and the theta variations. And most importantly, as R tends to zero, the stresses still go to infinity. So, though we have assumed plasticity, the infinite stresses at the crack tip. Remember why we came to plasticity, why we decided the plasticity must be there at the crack tip, because the elastic stresses given by the Williams solution told us that there's a 1 by square root r singularity, which will make the stresses go to infinity as r tends to zero. Infinite stresses cannot be sustained by the material, and therefore plasticity must exist. So even after we looked at the HRR fields, which take care of plasticity, large scale yielding at the crack tip, hardening, etc., we still see that the stresses go to infinity. So what is missing here? Obviously, we can't go into the details of this, but the missing elements are the following. The most important missing element is that the HRR fields are also just like the Williams fields, also assume small strain theory of plasticity. So they still assume that epsilon ij is given by half u I comma j plus j comma I. So these are the small strains. The small strain assumption is still valid for this, whereas in reality, in front of the crack tip, there is a region where the deformations are extremely large. So the picture may be something like this. So in front of a crack tip, you have a region which has very large deformations, and here small strain theory does not hold. So here small strain plasticity breaks down. You have to take geometrically nonlinear effects in this region. You have to take large deformation into consideration in order to analyze what happens within this region. But hopefully this region is now surrounded by a J dominant zone where the stresses vary according to what is given by the HRR fields. So these are called HRR fields, and the stresses vary as r to the power 1 by n plus 1, with J being the crack tip stress characterizing parameter. So, so this region of large deformation, which we have not analyzed so far, is there at the tip of the crack. This is small. This is engulfed in a J dominant zone, and you may have a K dominant zone around it also. And if this K dominant zone is much bigger than the J dominant zone, then the K that you have applied on this, K that you have K1, let's say that you have applied on this, will govern the J inside. But that is your small scale yielding. But it may happen that you don't have a K dominant zone. The J dominant zone is large, so that it's bigger than the K dominant zone, in which case you have large scale yielding. So you may have both. In the J dominant zone, you have the HRR fields. If you have a K dominant zone, here you have the K fields or the Williams fields, and that's the structure of the crack tip. This is a region which we have not analyzed, but we have seen that if we don't take this into account, then the displacements at the crack tip go to zero. The stresses still go to infinity, but if we take the large deformation in this yellow region into account, then the stress fields look somewhat like this. So this is the sigma 2 to the opening stress. This is your zone where large deformations are valid. So if you take this zone into account, do a real large deformation based finite element simulation, you will see that the stresses do not go to infinity anymore. They sort of drop down to a large but manageable value, realistic value. Then you have this plastic zone, which is dominated by J, and in this region the HRR fields holds, and this is the HRR field. And if you have small scale yielding, then outside this you might have the K field, the Williams 1 by square root R field taking over. You may or may not have this if the HRR field is too large and engulfs the and overwhelms the K field, then you may not have this region, but you almost always have a large deformation region, and then a HRR region, and then you might or might not have a K field. So the size of these regions are roughly this. So you can take delta t, the crack opening displacement, like we have calculated previously, you draw two 45-degree lines emanating from the crack tip, and this is your delta t. If this delta t, if you normalize this distance ahead of the crack tip with this delta t, then at about 2 delta t, your uh, large deformation region ends. So this large deformation region is of the size of roughly 2 delta t. 5 to 6 delta t, your HRR fields extend, and then you may or may not have a K field. Remember, delta t is proportional to J. So the crack becomes blunter and blunter as J increases, and therefore this point, as delta t increases, will move further and further to the right. So will this point. So uh, so this is the picture, this is the complete picture at the crack tip. This is what happens at the crack tip. This region is actually very important because it is where very large deformations occur. Deformations are extremely large in this region, and this is where material separation processes like void growth, void nucleation, etc., dislocation emission, and so on, all the damaging mechanisms that prepare the crack for its next move, they happen in this region. So this completes our picture of the crack tip fields in elastoplasticity, and in the next lecture we will look at how we can actually calculate the J and characterize JC.